Yesterday, we defined power as the rate at which work is done. What does that mean? It's not how much energy you expend in doing something, but rather it's how quickly you expend that energy. If I climb a flight of stairs, or if I climb, 100 flights of stairs from the ground floor to the top of a really, really high building, then I've done a lot of work. But if it takes me 4 hours to do it, then I haven't done that work that quickly. My power output would be quite low in that case. On the other hand, if I climb a flight of 1 stairs, that's to the second floor of this building, and I do it really quickly in a time of a second and a half, then my work isn't all that much, but my power output is very high because the rate at which I did the work is high. Power is not the amount that you do, but rather it's how quickly you do it. Now, you remember from yesterday that power is equal to work over time. If it's the rate, then it's got to have time on the bottom. If it's the rate at which work is done, then it's going to have work on the top. Do you guys remember what the units for power were? Two sets of units that we addressed yesterday. Yeah? Okay, the units are joules per second. And what's the other thing that means the same thing as joule per second? That would be the watt, which we usually just abbreviate by a W. So 1 joule per second would be exactly equivalent to 1 watt. Now, usually at this point, we would have an example problem. As I told you yesterday, your example problem today is going to be a problem that you collect data for yourself. The sample problem today is to find the power output of your legs. Now, how are we going to find the power output of your legs? Well, we're going to take work and divide it by the time. How are you going to find time? Easy. Measure the time that it takes to go up the stairs by using a stopwatch or just using the stopwatch timer on your phone. Okay, that's an easy one. How are you going to find the work that it takes you to climb up the stairs? Well, we know that work is equal to change in energy. How much energy do you have after you've reached the top of the stairs? What kind of energy do you have after you've reached the top of the stairs? Potential energy. So we're going to say the final energy is mgh, final. What kind of energy do you have at the bottom of the stairs before you go? Zero. You have no energy at the bottom. So we're going to say that work is equal to mgh final minus 0, or in other words, in this case, mgh final. Remember how in that other problem I said be careful, it's not always 1/2 mvf? Clearly, it's not always 1/2 mvf. Here it's mgh final. We find the work, and if you can find work, then all you got to do to find power is simply divide it by time. So our equation for this example that we're doing today ends up becoming mgh final over the time. Now, what we're going to do here is go out into the stairwell, and you guys are going to run up the stairs 2 at a time, run or walk up the stairs 2 at a time, independently of each other. We can keep going 2 at a time just so that we can filter people through a little bit faster here. Each person is going to be responsible for timing themselves. Now, you're also going to need to know what your mass is. We've got a scale, a bathroom scale in here that you can measure your mass if you don't know what your mass is. Okay, if you've got your driver's license recently, then your mass will be in kilograms, will be on your driver's license. Or if you just think you know what it is, then just use the number that you think it is. If you know what your weight is in pounds, then all you got to do is divide that by 2.2 to get your mass in kilograms. The only other thing we need here is the height of the stairs. When we go out there, we're going to come up with a way together of finding the height of the stairs. Remember, we don't want the length of the stairs, and we don't want the diagonal length of the stairs. Rather, we want this vertical height of the stairs. Okay, once we collect that data for the height together, then we will start running up the stairs, and we'll all use that same number for height, different numbers for time, and different numbers for mass. Once you've got your data collected, your job is to come into the classroom and then calculate your human power output. Now, quick question. Predictions here. The power output, let me define a term for you that you've heard before. 1,000 times or more. A horsepower. A horsepower is a unit of power. Now, it's loosely defined as the average power output of a horse. Although the power output of the average horse ends up actually being a little bit less than horsepower. So if you can manage to put out a horsepower as you're running up the stairs, it means for that short time that you're running up the stairs, you're more powerful than a horse. Not stronger than a horse necessarily. Not that you can do more work. Okay, I challenge you to plow a field. Okay, good luck with that. You're not going to do more work than a horse. Okay, but are you more powerful than a horse over a short period of time? Well, if your power output is greater than about 750 watts, then yes, you are more powerful than a horse over a short time. If your power output is less, then you're not. Let's make some predictions here. You take as many stairs as you want at a time, many as you want. How many people think the most powerful person in this room, okay, the most powerful person in this room, how many people think their power output is going to be between 0 and 50 watts? Nobody, all right? How many people think that their average power output of the most powerful person in the room is going to be between 50 and 100 watts? Okay, 3 of you. How many people think between 101 and 300 watts? 1, 2, 3, 4, 5, 6. I think I counted. And what about between 301 and 500? Now we're starting to get pretty powerful, right? Comparable to a horse, same order of magnitude. 1, 2, 3, 4, 5. And finally, whoops, we skipped one there. 501 to 750 watts. How many people think it's going to be in that range? Almost the power of a horse? Nobody? How many people think the person that has the highest power output is going to be more powerful than the average horse over the time that it takes them to climb the stairs? Greater than 750 watts. Nobody? All right. Okay, so most of us are guessing in this range right here of 100 to 500 watts. All right. You're going to go to the stairwell now. We've actually got 2 stairwells that we'll work with here. Actually, 3 stairwells that we'll work with. We'll go to the one right out here by the old kindergarten wing. Okay, we'll go to the one down by the shop, by the wood shop. And actually, no, the one down by the gym is not going to work for us. The reason being is because we have to have a way of being able to dangle a tape measure down from the top to the bottom. And you can't do that down by the gym, just with the way that the stairs are structured, right? So down by the wood shop or by the old kindergarten wing, let's say, so our maximum power output, Jonah, was 1,215 watts, which is about 1.5 horsepower. So the next time you see a car advertisement says it's this many horsepower, think back, okay? It's not that much more powerful than Jonah's. Well, okay, a car is a little more powerful than Jonah is. But next time you see a horse, you think, hey, Jonah could beat that horse. Jonah could take 1.5 of those horses up the staircase. All right, here's what I want you to do right now. Take a look at your power worksheet that was posted on Google Classroom the other day. We'll put it up on the board here as well. I want you to work on that power worksheet right now for the next probably about 10 minutes, please. All right, let's have a peek at question 5 and 6 here. 5 says a 2 kilogram box is pushed 20 meters with a force of 50 newtons, 8.5 seconds. What's the person's power output? We know, Zach, that power output is work over time, and work we know is F times D. So if we want, we can just sub in F times D over T if we want. Now, we could calculate work first and then plug the number into the equation, or we could just sub the equation into the equation. It doesn't really matter there. The force here is 50.0 newtons. The displacement here is 20.0 meters, and the time interval is 8.50 seconds. And when you do that, you should end up getting 117 watts. Anybody else get that? You got what, sorry? 118? Okay, I had 117, but if you guys are getting 118, I must have rounded wrong there. Okay, so 118 watts, good. All right, next one, 6 says a bicycle is pedaled at a speed of 20 kilometers per hour for 20 minutes. The power output of the cyclist is 400 watts. What's the average force that the cyclist applied on the bicycle? This one's a little bit trickier here. We got a power output. We have a speed here, which we're probably going to, if we use that, we're going to want to convert that to meters per second. And the minutes to seconds as well. Yes, you're right. Thank you. Let's write down those givens. We know that it's a power question. And if it's a power question, it's probably a work question as well, because power always involves work. We have a speed here of 22.0 kilometers per hour. Does anybody have that in meters per second? 22 times 1,000 divided by 3,600? 6.1? Is that exactly 6.1 or 6.111? Good, thank you. And my time interval here is 20 minutes, which we're going to convert that to seconds. 20 times 60 gives me 1,200 seconds. The power output is 400 watts. We want to find the average force here. Yeah, I think that's right. All right, what do you want to do here? What do you want to try for this? If it's a power question, let's try writing down the power equation. Power is equal to work over time. We know the power, right? We know the time. What's the speed? Wow, let's look at that, 6.11 for the speed there. Are we going to use that? Oh, we don't know the distance, do we? What are we going to do? There's two options here. What's one of them? Okay, so we could say V is equal to D over T. And we could solve for displacement that way. I think V times T. We got V, we got T. Solve for the displacement. Right here, we could solve for the work right here, given this and this. And then CW is equal to F times D to solve for F. Is that what you did? Yeah. Okay, good. The other option is to sub that equation, sub the equation for work. Just watch this. This is kind of neat, actually, what happens in this. Work is equal to F times D, right? Agreed? Now, all I've done so far really is what you were doing, right? Watch this. What's D over T? Velocity. So isn't power going to be equal to F times velocity? So if I've got the power and I've got the velocity at 6.11, can't I just find the force without even worrying about the displacement? Does that make sense? I'm doing the same thing as Danny was doing there. I'm just kind of doing it together in one step, and that ends up saving a little bit of time. But that's kind of a tricky thing to kind of come across. But notice how things sometimes just fall into place. Look, let's try something. Right? W is F times D. Let's sub it in, see what happens. Oh, look, V is equal to D over T, and I've got V. Maybe I can try that. And sure enough, it works out. We're going to end up with the same answer as Danny ends up with there. My method is just a tiny bit shorter. I end up getting 65.5 newtons. Danny, what did you get? 65.5 newtons. Go figure. It's not a coincidence, right?